Hello and welcome back to this tutorial. My name is Dr. Garuma Abdisa. In this tutorial we will talk about Newton's laws of motion. Newton's first law of motion. Let's begin by demonstrations. The first case we can consider is whenever no net external force acts on this ball seated on a tabletop, which is originally at rest. So as you can see, the ball doesn't start motion. As you can see, this ball continues in its state of rest until some external force acts and changes its state of rest. Next, we will see those external forces which may act on this ball which was originally at rest in order to change its state of rest. But for now, because any external unbalanced force is acting on the ball continues to sit on the tabletop. The second case is the ball sliding on a very rough surface. The surface is very rough, and because of its roughness, the ball came to rest only after traveling a small distance. A ball sliding on a very rough tabletop, such as this one, comes to rest because of the force that is acting on the ball from the opposite direction because of the roughness of the surface. After traveling only about 7.5 centimeters, this ball has stopped due to friction. Let us see the third case. Now, still, the surface is rough, but the roughness has decreased. It is less rough than the previous case. So, the ball now could travel a little further than the first case. So, a ball sliding on a rough table, in this moment which is less rough than before, after traveling only about 14 centimeters, it has now stopped due to friction. At least it has traveled twice as before. The fourth case is a ball sliding on a perfectly frictionless surface. This kind of example could be ideal because we cannot find such a perfect surface that is completely or perfectly frictionless. But if we were to find that kind of surface, this is what would have happened. The ball travels on a straight line for indefinite time. That is, it travels forever. A ball sliding on a perfectly frictionless table, now there is no friction and the ball travels forever. No additional force is required to sustain the motion. Thus, according to this law, if we could eliminate friction completely, the ball would never slow down, and we would need no additional force at all to keep the ball moving once it had been started. So, these are the formal statements of the first law of Newton. A body acted on by no net force moves with a constant velocity, which may be zero and zero acceleration. Or, every object will remain at rest, or in uniform motion in a straight line, unless compelled to change its state by the action of an external force. This statement is exactly what we have looked at with various cases using the demonstrations that I've shown you a while ago. This is simply the conclusion of those demonstrations stated in this formal statement. So keep note of the first law of Newton. Now we move on to Newton's second law of motion. Three variables are connected mathematically by Newton's second law. These are the force, mass, and acceleration. As usual, let us demonstrate the relationship before we come to the conclusion and set up some relationship between force, mass, and acceleration. The first case is we vary the mass and we fix force. It means that we apply equal magnitude of force on different sizes of a mass. For example, if we apply a force F on this mass, it accelerates. Now, the mass is smaller and the acceleration is larger. Now we take a bigger mass. This moment, if we apply the force, it accelerates less. As you saw it, now the mass is bigger and the acceleration was smaller. The conclusion from the first case demonstration is that for the same applied force, the smaller the mass, the larger the acceleration, and the larger the mass, the smaller the acceleration. Mathematically, acceleration is inversely proportional to mass, or in symbols, acceleration is inversely proportional to mass. The second case is now we vary force and fix the mass. It means that in this case now we keep the magnitude of the masses to be equal and we vary the magnitude of the applied forces, and we will see what would happen. The first case under this is I will apply this much amount of force to this mass and then it accelerates this much. This moment, the smaller the force, the smaller the acceleration. This moment I will apply a bigger force to the same mass. Now it accelerated a lot. It means that the bigger the force, the bigger the acceleration. A small force produces small acceleration, large force produces large acceleration. So what is the relationship between force and acceleration? It's direct. Very good. So mathematically, acceleration is directly proportional to force, or in symbols we write it this way and we'll read it as acceleration is directly proportional to force. Combining the two cases, from the first case we had acceleration is inversely proportional to mass, and from the second case acceleration is directly proportional to force, or acceleration is directly proportional to force and inversely proportional to mass, and we can combine and write the two equations as one in this form. By definition, 1 Newton is the amount of net force that gives an acceleration of 1 meter per second squared to a body with a mass of 1 kilogram. So, by choosing the proportionality constant to be 1, we can write A simply to be equal to force divided by mass. Or possibly, force is equal to mass times acceleration. Here is a formal statement of Newton's second law. Newton's second law of motion states that if a net external force acts on a body, the body accelerates. The direction of acceleration is the same as the direction of the net force. The mass of the body times the acceleration of the body equals the net force vector. So, the vector sum of all the forces acting on an object or on a system equals mass times acceleration. This is a formal statement of the Newton's second law of motion. Now let us see Newton's third law. A force acting on a body is always the result of its interaction with another body. So, forces always exist in pair. Assume, for example, we have a ball and you kick a ball. As you kick the ball also kicks back on your foot. Consequently, the ball accelerates, and because of the larger mass of our body, we don't accelerate in the reverse direction. Because our body is massive, the ball is accelerated. This is the force of the ball on the foot, and this one is the force of the foot on the ball. According to Newton's law, third law, these two forces have equal magnitude, but they are opposite in directions. These force pairs are called action and reaction forces, or action and reaction force pairs. Which one to call the action and which one to call the reaction force really doesn't matter. It is arbitrary. But what is important is that these two pairs of forces have always equal magnitude and opposite directions. Here are some important points to consider as we talk about Newton's third law of motion. The first one is forces always exist in pairs. Second important point, we can call either force as the action force and the remaining force as the reaction force. It is quite arbitrary. Thirdly, the action force and the reaction force act on different bodies. One of the bodies, as you saw in the demonstration, acts on the foot. The other force, if we call it the reaction, for example, acts on the ball. So these two forces act on two different bodies. One is on the foot, the other is on the ball. It's because of this reason that even if these two forces have equal magnitude and opposite in directions, they never cancel each other out. The fourth important point is the two forces have the same magnitude but are opposite in directions.